Okay, so let's continue with the solve problem on permutations. So in last lecture we finished what is permutation, and now we'll solve problem, and then we'll move to combinations. So here the problem says is that one person named Mr. Jones, and he wants to arrange 10 books and on a bookshelf, and there are four mathematics books, three are chemistry, two are history books, and one is a language book. So in total there are 10 books. You can see 4 plus 3 plus 2 plus 1, which is 10. And Jones wants to arrange his book so that all the books dealing with the same subject are together. So this simply means that mathematics books should be together, chemistry books should be together, history and language, so and so forth, right? So how many different arrangements are possible? So I have drawn this here. Like it's not said that first should be the mathematics books, then chemistry book. Don't take the order in the question. In the question it is given like there is an order of the books, but the question that is asked, what is asked to solve is like he just wants all books to be together of the same subject, right? So it doesn't matter whether math books are first or last or in the middle or whatever. Same holds for any other book like chemistry, history or language. So the order doesn't matter which should be first, but the thing that matter is chemistry books. If there are three, here we have three chemistry books, they should be together, right? And the same argument is valid for rest of the subjects. I hope things are clear in terms of what is being asked. Now, here, let's say I'm just saying that like math book is first. It doesn't matter, just to explain, right? So let's say math book is first, the order which is given in the question. But again, I'll repeat, the order doesn't matter, and we will see why. Okay, because it's not asked here, and we will see that we didn't consider order into picture. And if what happens if we consider order, we'll discuss all this. So firstly, let's say we have maths books. We have four math book. So of course we know that there are four factorial ways to have internal arrangement of these four books of mathematics. Similarly, for chemistry books, there are three factorial ways, then 2 factorial for history, and 1 factorial, of course, for language book. So, just to arrange in this order, we need, of course, we have to multiply all this, multiplication of all this, 4 factorial into, I'm not calculating the exact number, whatever is it, but at the end, we have to multiply all the factorials, 4 factorial, 3 factorial, 2 factorial, and 1 factorial to arrange this books, right? But now it is said that we need math books together, chemistry books together, history books together, and language book together. So what we can do? So as I said, order doesn't matter, right? So any of the combination is possible, right? So now consider this all four books of math as one single book. Similarly, let's consider the chemistry books, three books as one single book, one single unit, and similarly for the language book. So now we just have four books. One, two, three, four. Let's say we have one big giant book that we combine of all the particular subjects, and we have four books now. So what can be the arrangement of this four books? Four factorial ways, number of possible ways, and of course due to the basic principle of counting will multiply. So we know that internal arrangement of all these books will be this one, and again we have 4 factorial. So in total our answer will be the 4 factorial, which is this 4 factorial here, and multiplied with this 4 factorial into 3 factorial into 2 factorial and into 1 factorial, which is this one, right? And if you will use calculator, you will get 6192, I guess. Yes. So I hope things are clear that here order doesn't matter. If order should have mattered, then we shouldn't have considered the uh, 4 factorial into account, right? So this is how simple permutation problems can be solved. We will solve more questions as well, but later on I'll give and make lectures on it. Side by side, I will try to cover and finish the theory so that we can move ahead over in our playlist. So let's move towards combinations now. And let's say now, until now, we were given the objects, and we have to find possible ways of arrangement of that objects. But what if we have to select from particular objects, and then from that selected objects only we have to find the possible ways to arrange them? what does i what does that mean? Let me explain. Let's say we have five objects, right, or five letters, and we are asked like we have to maybe take three, let's say, select three. So what are the number of ways of selecting three letters from five letters and then arranging them? So let me write this statement, it will be better. Like oh, how many different groups of three could be formed or could be selected from five items? And those five items are A, B, C, D, and E. Oh, items. A, B, C, D, and E. So, of course, like let's try the very intuitive or the naive way to do the same, and it will be like initial item. We have five ways to select, right? We have to select three, right? So first can be selected in five ways because we have in total five. Then there are four ways to select the next item, and of course at the end three ways to select the third item, and we are done, right? We won't go to two into one because we have to just select three out of five. So this should be our ways of selecting the group of three, right? So ways, number of ways to select the group of three when order, of course, when order is relevant. Order in which items are selected is relevant. But there is one problem because this is not the answer. Why? Because for every group of three that we have from this five that will form, what will happen? There will be internal, let's say from A, B, C, D, E, we are selecting A, B, C, right? Then there will be for any particular group A, B, C, not we are selecting A, B, C, just for example, like there will be one of the group A, B, C. For this particular group A, B, C, there will be internal permutations as well, right? Like A, C, B, then, and we know that how many will be because there are three, so it will be 3 factorial equal to 6, right? So for every group of 3, then this will be counted 6 times. And so if we will do this, then it is wrong. We have to add something in here to find how many number of different groups of 3 can be selected from 5, because we don't want to consider ABC then ACB as well. We have to subtract all those ways, right? So what we will do for that? So of course we have to divide that by 3 into 2 into 1, because any group of 3 there will be 6 possibilities, so we have to divide by 3 factorial, or to be precise by 6. So let's generalize this. This is a naive way. You might know the combination, this thing NCR, which is like when we speak we write we say like NCR, and it is written like this. We just have like parenthesis little bit bigger and we write NCR. So it's like number of ways of selecting R items from N items, right? In total we have N and we are selecting R out of them. So what does this represent? NCR. So NCR represents the number of different groups of size r, that is here we took size 3, that can be selected from a set of size n, and when the order of selection is not relevant. So we doesn't matter like firstly we will pick first item or second item, whatever. Here also like the order doesn't matter, right? Then this is called NCR. Now there are two contradictory statements here. I said like this I wrote, and I wrote it here that the order of items is relevant. So what is this? Let's discuss this in a next video, that why I wrote this. But let me try to finish the derivation of this NCR. So in general, what we can write, now I'm writing in general terms, and I'll try to connect it to the particular problem of 5 versus like 3 selection from 5. So we'll see that. So in general, what we can say is that n into n minus 1, but we will not go until 1, we will go until n minus r plus 1. What is this? I'll discuss in a minute. So what does this represents? This represents the number of different ways that a group of r items could be selected from n items. And most important, when the order of selection is relevant. Now let me try to take up the curtains. Here I wrote order of items is relevant, but when I define NCR, I will define again formally in one of the next slide. I said order of selection is not relevant. What is this? So firstly let me go step by step. This what I wrote here is nothing but this thing, 5 into 4 into 3. If you will have n equals 5 and r equals to 3, you will get the same. You will like 5 into 4, and what is r? R is 3, right? So it's 5 minus 3 is 2, and plus 1 is 3. So this multiplication is nothing but these things. I just wrote in a generalized form. So when the order of selection is relevant, then we write these are the number of ways of selecting the r items from n items. When I'm emphasizing this term, when order of selection is relevant. And so because the first one can be selected in any of the n ways, then second one can be selected in remaining n minus 1 ways, then third one from remaining n minus 2 ways, and so on. And that's why we wrote this thing using basic principle of counting, everything multiplied. Now for each group that we form, these are total number of ways, right? Now as I said, I'm just repeating it in a generalized form, that for each group of r items that we form, these are the total number of ways, or total number of groups, sorry, of r items, like from n items. So what happens is that all r items will be counted r factorial times. This is what we saw here, that they were counted here 3, r was 3, so they were counted 6 times, or in general r factorial times. So that's why what we have to do, we have to divide this number that we got. So I'm writing with a new color here, that n into n minus 1 until n minus r plus 1, and we have to divide it by r factorial, right? So just to, so now we are neglecting that order of selection, like it doesn't matter like it's ABC or ACB or whatever, right? So that doesn't matter now, and that's why during the now this becomes the definition of NCR. How? Let me little bit modify it. So n into n minus 1, I'm just trying to make factorial in the numerator. So I will go until from n minus r up till 3, 2 and 1. I'm just writing 1 directly. So I have to divide as well by n minus r. Here I am writing 3, 2 up till 1. So basically this is nothing but n minus r factorial at the end. And it's the same thing, because since we multiplied we have to divide. So this is n minus r factorial. And we already had r factorial, right? But now the numerator here is, let me take a fresh page. Now the numerator becomes, because this is nothing but n minus 1 up till we are going up till 1, which is nothing but n factorial, right? And in the denominator we already have n minus r factorial, and r factorial was already there, and this you already studied in your high schools, that this is the definition of NCR. And now we will say that the order doesn't matter. So when we say this definition of NCR, we say that when we divide by r factorial, then we say that the order of selection doesn't matter here. Now let me write again the formal definition that I just spoke a few minutes before. Doesn't matter. Now what does this says? Let me write it quickly. That NCR represents number of different groups of size R that can be selected or formed from a set of size n, provided, again I am writing, when the order of selection doesn't matter or it's not considered. So again I'm just explaining, like let's say we have A, B, C, D, E, and we have to select 3 out of them. So whether we select A, B, C or B, A, C, like selecting B, then A and C, or firstly A, B and C, or C, A, B, this order should not matter. Whatever I take, if I take A, C, A, B, C or C, A, B, this will be counted as one. And this is what the definition of selection is. Now, in the very next lecture, I'll take a thorough example of this as well. It's the same thing that we did for permutation in this lecture, so that things become more clear. I hope the derivation is clear. It's little bit like tricky, not tricky, but yeah, you have to pay attention a bit. But I hope this will be helpful to you. So stay tuned and we'll see each other soon. Thank you.